Welcome to Mrs. Neller's notes for her pre-calculus class. These are the notes for section 3.7, day 2, entitled Rational Functions. And today we're going to talk more about how the different transformations can affect the graph and the asymptotes and the domain and range of a rational function. And then we're going to graph some of those types of rational functions. So we're going to talk about those three objectives right there. Now we kind of observed the asymptotes yesterday, and we talked about how they were either horizontal or vertical lines that the graph approaches but is never supposed to touch, even though sometimes it can cross over it. And here we're going to take, like it says up at the top, we're going to take a closer look at the behaviors of the vertical and the horizontal asymptotes today. And when we're dealing with our horizontal asymptotes, we need to focus on the degree of the numerator. And this we went over yesterday, okay? The degree of the numerator, if it's equal to the denominator, then we're going to use a ratio of the lead coefficients. So that's what's listed here. If the degree of the numerator is less than the denominator, then we'll just automatically use y equals 0. And if the degree of the numerator is greater than the degree of the denominator, we don't have any horizontal asymptote. Okay, so those are all the characteristics that are listed here. So really for horizontal asymptotes, there's three possibilities. Okay, if they're equal, if the degrees are equal, then you use the ratio of the lead coefficients. If it's less, the numerator is less than the denominator, then it's just automatically y equals 0. If the numerator is greater than the denominator, then there's none. And then for our vertical asymptotes, remember, it's the value that makes the denominator 0. So for this example here, example 4, we've got A and B, and then on the next slide we have C and D. And we're just going to take a look at finding those horizontal and vertical asymptotes. So we're not actually going to graph these. We're just going to focus on finding those horizontal and vertical asymptotes. Okay, now when you have really complicated rational functions like we do in part A, you have a trinomial over another trinomial. You want to factor first. So remember that is going to be your first step to factor. So for my numerator here, let's see, I'll need the factors of 3 and the factors of 1. So I'm going to set up my two sets of parentheses. I'll need a 3x and an x, and then I'll need the factors of 1. It's going to be a 1 and a 1. And I need my outer terms and then my inner terms to add up to a -2. So my outer terms would get me a 3. If I made that negative, I'd get a -3. And then my inner terms would be a 1. So if I added the 1, then the -3 and the 1 would add up to a -2. And then in my denominator, again, I'm going to have to factor. I need the factors of 2 and the factors of 2. So I'll need a 2x and an x. And then, let's see, I need my outers and my inners to add up to a 3. So outers, let's see, if I put a 2 here and a 1 here, then I could get an outers that would add up, or multiply to a 4. And my inners would be a 1. So if I had 4 minus 1, that would give me my middle term as a 3. Now notice that nothing cancels here after we factor this. So now that I have r of x factored, it's just an equivalent way to write the original rational function. And what this does is that it helps me find my horizontal and my vertical asymptotes. Okay? Horizontal asymptotes, the degree of the numerator and the degree of the denominator, they're the same. I have an x squared and an x squared. So when they're the same, I'm going to use the ratio of my lead coefficients. And that's easiest to see with the way the problem was originally written. So my horizontal asymptote, since it's horizontal, it's going to be y equals, and that's going to be the ratio of the lead coefficients, 3/2. Don't reduce it, just leave it 3/2. And then my vertical asymptotes, those are going to be the values that make the denominator 0. So that's easiest to see in my factored form here. And since these are vertical lines, they'll be x equals 1/2 and x equals -2, since those are the values that would make my denominator 0. And remember, you can find those by taking the stuff that's in each of these little parentheses and setting them equal to 0 and solving for x. Okay, for part B, I'm going to factor only in the denominator, because here in my numerator, I can't really do anything. There's no GCF to take out. It's not a difference of two squares. So I'm just going to leave the 2x minus 3 as is. But in my denominator, I have a difference of two squares. So that'll be x plus 1 times x minus 1. And again, my horizontal asymptote, I can find that by looking at the original problem. Here I see that the degree of the denominator is bigger than the degree of the numerator. So the way we were discussing that before is the degree of the numerator is less than the degree of the denominator. So that means it's just automatically y equals 0. And then for my vertical asymptotes, I'm going to get that information from my factored form here. It's the values that make my denominator 0. So it's going to be x equals -1 and x equals +1. Okay, so once you get the hang of these and once you know what you're looking for, they go relatively quickly. Okay, for part C, I'll be able to factor the numerator and the denominator here. For the numerator, I can take out a greatest common factor, which is an x squared, and that'll leave me with an x plus 3. And then in my denominator, that's another difference of two squares. So x minus 2 and x plus 2. Remember, it doesn't matter if you write the x plus 2 first or the x minus 2 first. It doesn't matter. Okay, now for my horizontal asymptote, I'm going to look at the degree of my numerator and denominator. The degree of my numerator is actually greater than the degree of my denominator. So when that happens, I have no horizontal asymptote. And then for my vertical asymptote, that I can see best in the factored form. It's the values that make the denominator 0. So that'll be x equals 2 and x equals -2. Okay, and then one more to practice this in part D. The only thing I can do in my numerator here is to take out a GCF, so I'll take out a 2. So that's pretty easy. My denominator now, I have another trinomial, so I'll have to do guess and check. So I need an x and an x, and then the factors of 1, that'll get me to a 1. Actually, I don't think that one's factorable. You could possibly factor it, using the quadratic formula, but we would end up getting probably an imaginary number. So here, let's just leave it x squared plus x plus 1. Okay, and how that's going to affect our work is not so much for the horizontal asymptote. The horizontal asymptote, let's see, the degree of the numerator is a 1. So that's less than the denominator, which is 2. So that means it's just automatically going to be y equals 0 for my horizontal asymptote. And then for my vertical asymptote, since I have this special case here where I couldn't factor the denominator, I'm just going to put none. And I could factor it with the quadratic formula, but I'm going to end up getting an imaginary number. And we don't want to worry about that. We can't graph an imaginary number on our standard x and y coordinate plane. Okay? So these are the first few steps that we're going to be using when we're going through our graphs now and graphing our rational functions. And we still want to look for that information that we were looking for in the previous section of notes in 3.7 day 1. But we're going to start by factoring, just like we did. Um, you can find your horizontal and your vertical asymptotes. You want to find your x and your y intercepts, and then you want to go ahead and make your graph. Now, the book recommends it here in this order where you factor and find your intercepts and then your asymptotes. Okay, really you can go in any order you want. We can also write down our domain and range like we were in the previous day's notes. Remember, the domain and range are going to be connected to the horizontal and the vertical asymptotes. Okay, so let's go through example 5 here. This is our last one for today. And this is just a very thorough process of everything that we've had to do so far. All those little pieces that were listed in the previous table we're going to go through now. So our first step is to take this big function here and factor it. So in my numerator, I have 3 terms. So I'm going to do guess and check. So I'll have my 2 sets of parentheses, and I need the factors of 2, so that'll be 2x and x, and my factors of 4, and I have to get my outers and inners to add up to 7. So factors of 4. If I do a 4 here, when I check my outers, that would get me an 8 when I multiply them. So if I did 4 and 1, my outers would be 8 and my inners would be 1. And I'm trying to get them to add up to a positive 7. So if I make the 8 positive and the 1 negative, there's my correct factorization. And in the denominator, again, another guess and check. So I need the factors of x squared, which are x and x. And then I need the factors of 2. So that's going to be a 2 and a 1. And I need them to add up to a positive 1. So I'm going to need the 2 to be positive and the 1 to be negative. Now notice that nothing cancels. We're not going to see much cancellation in our types of problems. Okay? So we're done with the factoring step. Now, when we go on to the next step, that's finding our x and y intercepts. Remember to find your y-intercept. You can plug 0 in for x. So you can have 2 times 0 squared, so that's 0. And then 7 times 0 is 0, minus 4. And then you'd have 0 squared is 0, plus 0 minus 2. So that's going to be negative 4 over negative 2, so that's just going to be 2. So your y-intercept is going to be 2. Equals. And we can write that as an ordered pair. We could write 0, 2. That's probably the most appropriate way to write it. And then for our x-intercepts, remember this is where you want to find the values that make the numerator 0. So set your numerator equal to 0, basically. So our original numerator, you could think of it a couple different ways. You could take your original numerator was the 2x squared plus the 7x minus the 4 and set it all equal to 0. But you have to factor it, and we factored it on the previous slide. That work is shown. And then you set each of those equal to 0 and solve each of those little parentheses. So you get 1/2 and negative 4. Okay, so your x-intercepts then would be 1/2, 0, and then negative 4, 0. And a common mistake is for students to just look on their graphing calculator and try and find the ordered pairs. And a lot of times you don't have your settings on your table values set for halves or for decimals of any kind. So students will get the negative 4 value, but they won't get the 1/2 value. So that's why doing it algebraically and setting the whole numerator equal to 0 will help you find all of your values that you need. Okay, so now I'm going to take a look at my horizontal asymptote and then my vertical asymptote. Remember, the horizontal asymptote, I want to look at the degree of the numerator and then the degree of the denominator. So the degrees of the numerator and denominator, they were the same. So when that happens, then I'm going to use a ratio of my lead coefficients. Okay, horizontal lines are always y equals. So I have 2 over 1. basically is the ratio here. So my horizontal asymptote is going to be y equals 2. And then for my vertical asymptote, this is where I want to find the value that makes the denominator 0. And we factored the denominator before. We had x plus 2 times x minus 1. So the values that would make the denominator 0 then are going to be negative 2 and positive 1. So now this little note here about behavior near the vertical asymptotes, this your book focuses on more. This is where they have the notation that says as x approaches negative 2 from the left, y will approach negative infinity. Or as x approaches negative 2 from the right, y is going to approach positive infinity. Okay, so it's the behavior near those vertical asymptotes. And then the book will also say that as x approaches 1 from the left, y is going to approach negative infinity. And as x approaches 1 from the right, y is going to approach positive infinity. But how we address that when we graph is we do some test points. So that part there about the end behavior doesn't necessarily have to be noted. Your book makes a point out of writing all of that down. But the best way to approach that with least confusion is just to make a table of values and then test a few points. So if I have my axes here on my graph, okay, next thing I'm going to draw in is going to be my horizontal and my vertical asymptotes. Let's see, my horizontal asymptote was at 2. I'm going to put my dashed line in. And if you want to do multicolored graphs, that's completely okay. You can do colored pencil or highlighter, marker, whatever you need to, if you need to visually distinguish these areas. Okay, so I've got my horizontal asymptotes and my vertical asymptotes in. We had 2 vertical asymptotes, negative 2 and 1, so now they're all drawn in there. And now to find the end behavior, okay, when I graph it, this means that I'm going to pick a value on the left of negative 2. So I'm going to pick like negative 3. And if I plug negative 3 in to this original function, I get a value out that's less than 2. So I actually can put my intercepts in as well. Let's see, where were my intercepts? I had my y-intercept was at 2, 2. And then my x-intercepts were at negative 1, 2, 3, 4. And at 1/2. Okay. So this also confirms that if I pick the value negative 4 and put it back into the original function, I get 0 out. Okay, so that tells me that this part of the graph is going to stay to the left and below my horizontal and my vertical asymptotes. Okay, and if I test a value next to negative 2, but on the right side of it, so I want to pick like negative 1 or like negative 1.5. If I plug negative 1 into this original function, I'm going to get a value out that's greater than 2. So that means that this part of the graph is starting up high on the y-axis. And then you can see that I actually cross the horizontal asymptote and then go down towards my other vertical asymptote. So in this middle region here, my graph does a little bit of a curve. And again, the horizontal asymptotes are, and even the vertical ones, are meant to be places that the graph shouldn't touch, but sometimes in the middle you're going to see this where the graph actually does cross it. Remember, this is a dashed line, so there's openings there. And all the behaviors that we're discussing are technically behaviors that are at the extremes of the graph. So at the extreme positive infinity end, this graph is never going to touch the horizontal asymptote, and or vertical asymptote. And at negative infinity down here, as we keep going down towards negative infinity, this part of the graph is never going to touch the vertical asymptote, but it might have to cross it there in the middle. So that's okay if you see that behavior. And then I have one more region that I have to test. I have to go on the other side of my second vertical asymptote. So if I put a value like 2 or 3 or 4 and put it into the original function, I'm going to get a value out that is greater than 2. So that tells me that this part of the graph is going to be up here. And again, you can make a table of values where you are putting in x and then r of x, where you are putting in those values and seeing what you get out, and that can help you. So we tested, what was it, -3 and then -1, because those are on either side of my -2 value for my vertical asymptote. And then you could test 0, or you could test 2. Okay, but I don't want to lock you into thinking that you only have to think of whole numbers. You can do decimals, you can do more values to the left or to the right. Okay, and then those values that you get out, basically we're not concerned with what so much they are, but we're concerned that it's a negative value, or it's below or above the horizontal asymptote. So this value will be below the horizontal asymptote. Okay, this value is above it. This value is going to be, well, at 0 it's kind of on it, but it's also moving to below. And then for this one, it's above the horizontal asymptote. Okay, so that's what our graph looks like now. And the last thing we're going to make note of is our domain and our range. So our domain, remember, that's connected to all of our x values. So that's going to be pretty much everything except our vertical asymptotes. X can't be -2, whoops, or 1. And then for my range, that's all our y values. So that's going to be pretty much all of my y values except for whatever my horizontal asymptote is. Except for this graph, I actually do get a value. I do get that 0, 2 value out. So here, it's all real numbers because I do cross over that horizontal asymptote. Okay, if my graph didn't cross that horizontal asymptote, then that would be the exclusion for our range. We would say all the y values except for 2, except for y equals 2. But here, since we cross over it, it's all real numbers. Okay. So there's the book version of the graph. There's their table of values with their actual decimals. So I know I didn't complete mine on the previous page, but there's their completed table of values. And these are the problems that I would like you to practice so that you can get these concepts of the horizontal and vertical asymptotes down. You have to know the 3 characteristics for your horizontal asymptotes, and you have to know how to get your vertical asymptote. So you have to have those concepts memorized. And the best way to get them into your brain is just to practice, practice, practice. And if you have any questions, come on in and see me before school.